In mathematics, a root of unity, occasionally called a de Moivre number, is any complex number that gives 1 when raised to some integer power n. Roots of unity are used in many branches of mathematics, and are especially important in number theory, the theory of group characters, and the discrete Fourier transform. In field theory and ring theory, the notion of root of unity also applies to any ring with a multiplicative identity element. Any algebraically closed field has exactly n nth roots of unity, if n is not divisible by the characteristic of the field. General definition: an nth root of unity, where n is a positive integer, is a number z satisfying the equation. Traditionally, z is assumed to be a complex number, and subsequent sections of this article will comply with this usage. Generally, Z can be considered for any field R, or even for a unital ring. In this general formulation, an nth root of unity is just an element of the group of units of order n. Interesting cases are finite fields and modular arithmetics, for which the article root of unity modulo n contains some information. An nth root of unity is primitive if it is not a kth root of unity for some smaller k. Elementary facts: every nth root of unity z is a primitive nth root of unity for some R where 1 a per mole currency a per mole currency n. If z1 equals 1 then z is a primitive first root of unity, otherwise if z2 equals 1 then z is a primitive second root of unity, otherwise. And by assumption there must be a 1 at or before the nth term in the sequence. If z is an nth root of unity and a per mole b then z equals zb. By the definition of congruence, a equals b plus kn for some integer k. But then. Therefore, given a power z of z, it can be assumed that 1 a per mole currency a per mole currency n. This is often convenient. Any integer power of an nth root of unity is also an nth root of unity. Here k may be negative. In particular, the reciprocal of an nth root of unity is its complex conjugate, and is also an nth root of unity. Let z be a primitive nth root of unity. Then the power z, z2, a euro zn a euro a1, zn equals z0 equals 1 are all distinct. Assume the contrary, that z equals zb where 1 a per mole currency a, b a per mole currency n. Then zb euro a equals 1. But 0, b n, which contradicts z being primitive. Since an nth degree polynomial equation can only have n distinct roots, this implies that the powers of a primitive root z, z2, a euro zn a euro 1, zn equals z0 equals 1 are in fact all of the nth roots of unity. From the preceding facts it follows that if z is a primitive nth root of unity. If z is not primitive there is only one implication. An example showing that the converse implication is false is given by: let z be a primitive nth root of unity and let k be a positive integer. From the above discussion, zk is a primitive root of unity for some a. Now if zk equals 1, k must be a multiple of n. The smallest number that is divisible by both n and k is their least common multiple, denoted by LCM, n, a euro k. It is related to their greatest common divisor, GCD, n, a euro k, by the formula. That is. Therefore, zk is a primitive nth root of unity where. Thus, if k and n are k', zk is also a primitive nth root of unity, and therefore there are n, distinct primitive nth roots of unity. In other words, if R, n, is the set of all nth roots of unity and P, n, is the set of primitive ones, R, n, is a disjoint union of the P, n. Where the notation means that D goes through all the divisors of n, including 1 and n. Since the cardinality of R, n, is n, and that of P, n, is I, n, this demonstrates the classical formula. Examples: De Moivre's formula, which is valid for all real x and integers n, is: setting x equals 2 euro per n gives a primitive nth root of unity. But for k equals 1, 2, a euro, Na1. This formula shows that on the complex plane the nth roots of unity are at the vertices of a regular n-sided polygon inscribed in the unit circle, with one vertex at 1. This geometric fact accounts for the term cyclotomic in such phrases as cyclotomic field and cyclotomic polynomial. It is from the Greek root cycloplastomos. Euler's formula, which is valid for all real x, can be used to put the formula for the nth roots of unity into the form. It follows from the discussion in the previous section that this is a primitive nth root if and only if the fraction kn is in lowest terms, that is that k and n are coprime. The roots of unity are, by definition, the roots of a polynomial equation and are thus algebraic numbers. In fact, Galois theory can be used to show that they may be expressed as expressions involving integers and the operations of addition, subtraction, multiplication, division, and the extraction of roots. The equation z1 equals 1 obviously has only one solution, plus 1, which is therefore the only primitive first root of unity. It is a non-primitive second, third, fourth root of unity. The equation z2 equals 1 has two solutions, plus 1 and a 1. Plus 1 is the primitive first root of unity, leaving a 1 as the only primitive second root of unity. It is a non-primitive fourth, sixth, eighth root of unity. The only real roots of unity are a plus or minus 1. All the others are non-real complex numbers, as can be seen from de Moivre's formula or the figures. The third roots satisfy the equation z3 or 1 equals 0. The non-principal root plus 1 may be factored out, giving z2 plus z plus 1 equals 0. Therefore, the primitive cube roots of unity are the roots of a quadratic equation. The two primitive fourth roots of unity are the two square roots of the primitive square root of unity, a 1. The four primitive fifth roots of unity are. The two primitive sixth roots of unity are the negatives of the two primitive cube roots. Gauss observed that if a primitive nth root of unity can be expressed using only square roots, then it is possible to construct the regular n-gon using only ruler and compass, and that if the root of unity requires third or fourth or higher radicals the regular polygon cannot be constructed. The seventh roots of unity are the first that require cube roots. Note that the real part and imaginary part are both real numbers, but complex numbers are buried in the expressions. They cannot be removed. See casus irreducibilis for details. One of the primitive seventh roots of unity is where I per mil and I per mil 2 are the primitive cube roots of unity exp, 2 I I/3, and exp, 4 I/3. The four primitive eighth roots of unity are a plus or minus the square roots of the primitive fourth roots, a plus or minus I. One of them is. See heptadecagon for the real part of a 17th root of unity. Periodicity: if Z is a primitive nth root of unity, then the sequence of powers, a euro z1, a euro z0, a euro z1, a euro, is n-periodic, and the n sequences of powers, sk, a euro, a euro z car, a 1, a euro z car 0, a euro z car 1, a euro, for k equals 1, a euro, a euro n are all n-periodic equals z car j. Furthermore, the set S1, a euro, a euro Sn of these sequences is a basis of the linear space of all n-periodic sequences. This means that any n-periodic sequence of complex numbers, a euro z1 a euro xo a euro x1, a euro, can be expressed as a linear combination of powers of a primitive nth root of unity. For some complex numbers x1, a euro xn and every integer j. This is a form of Fourier analysis. If j is a time variable, then k is a frequency and xk is a complex amplitude. Choosing for the primitive nth root of unity, z equals e2 I n equals cos, 2 I per n, plus eo sin, 2 I per n, allows xj to be expressed as a linear combination of cos and sin. Xj equals ak, also known as cos, 2 I a jar kn, plus akb ka sin, 2 I euro a jar kn. This is a discrete Fourier transform. Summation lets senior, n, be the sum of all the nth roots of unity, primitive or not. Then, for n equals 1 there is nothing to prove. For n greater than 1, it is intuitively obvious from the symmetry of the roots in the complex plane. For a rigorous proof, let Z be a primitive nth root of unity. Then the set of all roots is given by Zk, k equals 0, a euro 1, a euro euro, a euro na1, and their sum is given by the formula for a geometric series. Let Sp, n, be the sum of all the primitive nth roots of unity. Then, where I1/4, n, is the Marr paragraph bias function. In the section Elementary Facts, it was shown that if R, n, is the set of all nth roots of unity and P, n, is the set of primitive ones, R, n, is a disjoint union of the P, n. This implies, applying the Marr paragraph bias inversion formula gives. In this formula, if D, n, then SR, nd, equals 0, and for D equals n, SR, nd, equals 1. Therefore, Sp, n, equals I1/4, n. This is the special case Cn, 1, of Ramanujan's sum Cn, s, defined as the sum of the sth powers of the primitive nth roots of unity. Orthogonality, from the summation formula follows an orthogonality relationship, for j equals 1, a euro n and jar euro squared equals 1, a euro n. Whereas the Kronecker delta and z is any primitive nth root of unity. The na euro a euro n matrix U-Housseth entry is defines a discrete Fourier transform. Computing the inverse transformation using Gaussian elimination requires n3 operations. However, it follows from the orthogonality that U is unitary. That is, and thus the inverse of U is simply the complex conjugate. The straightforward application of U or its inverse to a given vector requires n2 operations. The fast Fourier transform algorithms reduces the number of operations further to na euro log euro shn. Cyclotomic polynomials. The zeros of the polynomial are precisely the nth roots of unity, each with multiplicity 1. The nth cyclotomic polynomial is defined by the fact that its zeros are precisely the primitive nth roots of unity, each with multiplicity 1. Where z1, a euro z2, a euro z3, a euro xi, n, are the primitive nth roots of unity, and I, n, is Euler's totient function. The polynomial In, Z, has integer coefficients and is an irreducible polynomial over the rational numbers. The case of prime n, which is easier than the general assertion, follows by applying Eisenstein's criterion to the polynomial and expanding via the binomial theorem. Every nth root of unity is a primitive dth root of unity for exactly one positive divisor d of n. This implies that this formula represents the factorization of the polynomial Zn1 into irreducible factors. Z1 equals Za1, Z2 equals A, Z plus 1, Z3 equals A, Z2 plus Z plus 1, Z4 equals A, Z plus 1, A, Z2 plus 1, Z5 equals A, Z4 plus Z3 plus Z2 plus Z plus 1, Z6 equals A, Z plus 1, A, Z2 plus Z plus 1, A, Z2A Z plus 1, Z7 equals A, Z6 plus Z5 plus Z4 plus Z3 plus Z2 plus Z plus 1, applying Marr paragraph bias inversion to the formula gives. Where I1/4 is the Marr paragraph bias function. So the first few cyclotomic polynomials are, I1, Z, equals ZA1, I2, Z, equals A, ZA1, A1 equals Z plus 1, I3, Z, equals A, ZA1, A1 equals Z2 plus Z plus 1, I4, Z, equals A, Z2 A1, A1 equals Z2 plus 1, I5, Z, equals A, ZA1, A1 equals Z4 plus Z3 plus Z2 plus Z plus 1, I6, Z, equals A, Z3 A1, A1A, Z2 A1. A1A, ZA1, equals Z2A Z plus 1, I7, Z, equals A, ZA1, A1 equals Z6 plus Z5 plus Z4 plus Z3 plus Z2 plus Z plus 1. If P is a prime number, then all the pth roots of unity except one are primitive pth roots, and we have. Substituting any positive integer of permel 2en for Z, this sum becomes a base Z rep unit. Thus a necessary condition for a rep unit to be prime is that its length be prime. Note that, contrary to first appearances, not all coefficients of all cyclotomic polynomials are 0, 1, or a 1. The first exception is I105. It is not a surprise it takes this long to get an example, because the behavior of the coefficients depends not so much on n as on how many odd prime factors appear in n. More precisely, it can be shown that if n has one or two odd prime factors, then the nth cyclotomic polynomial only has coefficients 0, 1 or a 1. Thus the first conceivable n for which there could be a coefficient besides 0, 1, or a 1 is a product of the three smallest odd primes, and that is 3 or 5 or 7 equals 105. This by itself doesn't prove the 105th polynomial has another coefficient, but does show it is the first one which even has a chance of working. A theorem of Share says that there are cyclotomic polynomials with coefficients arbitrarily large in absolute value. In particular, if n equals P1a P2a a Pt, where P1, P2, a Pt are odd primes, P1 plus P2, Pt, and T is odd, then 1at occurs as a coefficient in the nth cyclotomic polynomial. Many restrictions are known about the values that cyclotomic polynomials can assume at integer values. For example, if P is prime and a Ip, D, then either dA permel 1, or dA permel 0. Cyclotomic polynomials are solvable in radicals, as roots of unity are themselves radicals. Moreover, there exist more informative radical expressions for nth roots of unity with the additional property that every value of the expression obtained by choosing values of the radicals is a primitive nth root of unity. This was already shown by Gauss in 1797. Efficient algorithms exist for calculating such expressions. Cyclic groups. The nth roots of unity form under multiplication a cyclic group of order n, and in fact these groups comprise all of the finite subgroups of the multiplicative group of the complex number field. A generator for this cyclic group is a primitive nth root of unity. The nth roots of unity form an irreducible representation of any cyclic group of order n. The orthogonality relationship also follows from group theoretic principles as described in character group. The roots of unity appear as entries of the eigenvectors of any circulant matrix, that is matrices that are invariant under cyclic shifts, a fact that also follows from group representation theory as a variant of Bloch's theorem. In particular, if a circulant Hermitian matrix is considered, the orthogonality property immediately follows from the usual orthogonality of eigenvectors of Hermitian matrices. Cyclotomic fields. By adjoining a primitive nth root of unity to Q, one obtains the nth cyclotomic field Q, exp, to I_in. This field contains all nth roots of unity and is the splitting field of the nth cyclotomic polynomial over Q. A field extension Q, exp, to I_iq has degree I, n, and its Gauss group is naturally isomorphic to the multiplicative group of units of the ring Znz. As the Gauss group of Q, exp, to I_iq is abelian, this is an abelian extension. Every subfield of a cyclotomic field is an abelian extension of the rationals. It follows that every nth root of unity may be expressed in terms of k roots, with various k not exceeding I, n. In these cases Gauss theory can be written out explicitly in terms of Gaussian periods. This theory from the Disquisitions Arithmeticae of Gauss was published many years before Gauss. Conversely, Every abelian extension of the rationals is such a subfield of a cyclotomic field This is the content of a theorem of Kronecker, usually called the Kronecker-Weber theorem on the grounds that Weber completed the proof. Relation to integer rings: for n equals 2, both roots of unity 1 and a 1 belong to Z. For certain n corresponding roots of unity are quadratic integers, for n equals 3, 6 they are Eisenstein integers. For n equals 4 they are Gaussian integers, see imaginary unit. For n equals 5, 10, neither of non-real roots of unity is a quadratic integer, but the sum z plus z equals to a res of each root with its complex conjugate is an element of the ring Z, 1 plus ℏ5/2. For two pairs of non-real fifth roots of unity these sums are inverse golden ratio and minus golden ratio. For n equals 8, for any root, z plus z equals to either a plus or minus 2, 0, or a plus or minus ℏ2. See also, Argand system, circle group, the unit complex numbers, group scheme of roots of unity, primitive root modulo n, Dirichlet character, Ramanujan sum, notes. References: Lang, Serge, Algebra, Graduate Texts in Mathematics 211, New York, Springer Verlag, ISBN A978-0-387-95385-4, ZBLA 0984.00001, MRA 1878556. Milne, James S. Algebraic Number Theory. Course notes are, Milne, James S. Class Field Theory. Course notes are, Nijkerk, Jar 1/4 Gen, Algebraic Number Theory, Grandelier and Der Mathematician was sent Schaffen 322, Berlin, Springer Verlag, ISBN A978-3-540-65399-8, ZBLA 0956.11021, MRA 1697859. Nijkerk, Jar 1/4 Gen. Class Field Theory. Berlin, Springer Verlag. ISBN A3-540-15251-2. Washington, Lawrence C. Cyclotomic Fields. New York, Springer Verlag. ISBN A0-387-94762-0. Derbyshire, John. Roots of Unity. Unknown quantity. Washington, D.C. Joseph Henry Press. ISBN A0-309-09657-X. Further reading, Storer, Thomas. Cyclotomy and Difference Sets. Chicago, Markham Publishing Company. ZBLA 0157.03301A.